Now we've connected a ring resonator between the power sensor and the signal source, and this ring resonator has been designed for a frequency of 3 gigahertz. This 3 gigahertz is the frequency at which the dimensions of the ring resonator, the total circumference of the ring resonator, is a multiple of the wavelength of the propagation velocity at 3 gigahertz. So we can find out the dimension of the ring resonator, we can measure the frequency, and from there we can find out the effective dielectric constant of this substrate being used. This is a very popular method for measuring the substrate epsilon r, as well as by measuring the bandwidth of the passband characteristics. We can measure the loss tangent and the attenuation characteristics on this ring resonator. We observe that we are in the passband of this ring resonator right now. As we change the frequency, the power level will drop from -1 dBm to -25 dBm, and as we go on the either side, the power drops considerably. It shows that it resonates at one precise frequency, and we can accurately determine the effective electric constant of this substrate. A similar half-wave resonator is also being provided. This half-wave resonator also resonates at the half wavelength of the propagation velocity on this particular substrate. This particular resonator has got some edge effects at the point of discontinuity, and because the gap is sizable and the coupling is small, the insertion loss in the passband is large as compared to a ring resonator. Now we have connected, and we can see that in the passband this ring resonator is going to allow a power to pass through, and in the other bands it will stop the flow of power. Similarly, we can find out using this thing also to measure the effective dielectric constant of the substrate being used. These are the Wilkinson power dividers. We can use these Wilkinson power dividers. As you can see that they comprise of the power being coming at port number 1, and it is being equally divided. These are designed for a frequency of 3 gigahertz, at which the dimension of this half path of the circumference is a half wavelength at the design frequency. The impedance at the beginning of the microstrip is 50 ohms, then it converts into 100 ohms and is again being converted into 50 ohms microstrip widths. We can observe that first of all we measure the direct power. We test it at a frequency of say 3 gigahertz at which we have designed. We observe that the direct power is plus 4.8 dBm in this case. Now we connect this source to the input of the power divider, and we connect the sensor at other port. We need to terminate the other end unused of the Wilkinson power divider into a 50 ohm termination. So the power drops from plus 4.8 to plus 2.2 dB. So roughly about 2.5 dB is the power division in both the planes. We can also use a directional coupler to find out the reflection coefficients at each of these ports in the pass band as well as off the design frequencies. We have also provided you with a Wilkinson unequal power divider. It is similar to the equal power divider only in that one port number 3 has a lesser amount of power, while the port number 2 has higher amount of power. And we can measure the parameters of S12 in the similar fashion. Now we are trying to measure S12. So plus 4.8 dB was our reference power. We need to terminate, and we can find out the different port parameters. Now we observe that once we have terminated, plus 3 dBm is available here, so about 1 dB is the insertion loss between ports S1 and 2, while if we replace the ports at the port number 3, a lesser amount of power will be available. We always need to make sure that the unused ports of all these devices have to be terminated into 50 ohms match loads provided. So we observe that the power available at the other port is lesser as compared to power available at port number 2.